Hi, hello, welcome to this third video on Mininet. In this video, we will talk about the high-level API of Python in Mininet to actually build customized topologies. So actually a topology you want, you can customize it and you can create it. And you will have an exercise to do creating a fat tree topology uh, in class. So the idea is that you create the topology in class and you learn how to do it, and you will have some time in the class to do it, okay? But first, let's see an example on how this high-level API works with this linear topology. So remember that the linear topology is actually one topology that we saw in the last video, and it's a topology where you create the same number of switches as hosts, and each host will be connected to one switch, and then the switches are connected between them, right? So there is, for instance, here, switch 1 connected to host 1, switch 2 connected to host 2, and so on, until switch n, and then switch 1 is connected to the switch 2, the switch 2 to the switch 3, and so on, up to the switch n. So let's see the code on the API of this topology. But first, before that, let's go to the terminal. I am on the Mininet virtual machine. As I showed you in the video, one can connect from the host operating system to the guest one, to the virtual machine of Mininet. And here I already connected that I am on the virtual machine of Mininet. And remember that to create a linear topology, for instance, with, I don't know, 5 nodes, I just use the command sudo mn ---- topo linear with a parameter of 5, an argument of 5 here. So I create, as you can see here, one controller, 5 hosts, 5 switches, and the connection between host 1, switch 1, host 2, switch 2, host 3, switch 3, host 4, switch 4, host 5, switch 5, and then the connection among the switches, switch 1 connected to switch 2, switch 2 to switch 3, switch 3 to switch 4, and switch 4 to switch 5. And then I can make a pingle here to see that all the connectivity is working correctly, okay? So this is more or less how the linear topology works. Let's go and see how the code of this linear topology works. So this is a high-level API program in Python, and here you have to import from Mininet topo the topo, which is the main class of topology in Mininet. Have also to import from Mininet.net what we call Mininet, and we will see how to use it later. I will import also the iRange node connections that I will show you in a minute, and then a login parameter. Okay, so I have here in the class, to start the code, I will create a class, and this class will be the linear topology. Okay, the linear topology will be called linear topo, and it, as you know in Python, it will inherit from the topo main class, which is the main class of topology in Mininet. So this is a linear topology that will have k switches with one host per switch. This is the constructor of the class. As you should, if you don't, please review a little bit object-oriented programming in Python and how to use constructors, for instance, in Python. This constructor will have as a parameter the k, the number of switches that I want, switches and hosts that I want in the linear topo, and an optional parameter called opts. Okay, the first thing that I do is I, let's say, call the constructor of the father class, which is topo, and I will not pass any parameter to it. So just this line is just to call the constructor of the father class, which is topo. Then I will put in in the self class of the object, the k parameter, and I will assign none to the last switch. So at the beginning, I don't have a last switch, so that is what I call it none. Then I run a for from in I from 1 to k. So I will run a for from the number of switches or hosts that I have, and I will create for each time of the host, I will add a host with the number I, which is the actually counter of the loop, of the for loop. So the first time I will create H1, the second time H2, third time H3, and so on till K. I do the same with the switches. So with the switches, I will add the switch 1 and switch 2 and switch 3. And remember that each host is connected to each switch. So I will connect in each time the for loop runs, I will create a link between the host and the switch. And what is missing, I'll have to connect the switches, the switch 1 with switch 2, switch 2 with switch 3, and so on. So each time, if I have a last switch, the first time I don't have a last switch, right? But for instance, the first time I don't have a left switch, so it will enter to this if, and the first switch 1 will be assigned a switch. Then the second time I will have a last switch, which will be switch 1, and then I will add a link between switch, which will be switch 2 and switch 1. And I will update last switch to be switch 2. And I will do this all the times until this for loop ends. So I create all the connection between the host and the switches and between the switches among the switches themselves, okay? I run a simple test here just to see if the topology is okay. So I create a topology I will call topo with linear topo. Remember, the linear topo is the class I just programmed. With a parameter of 4, I can put any parameter I want actually here. I will create the Mininet. To create the net, you use the Mininet class, and inside the Mininet, you put the topology that you want to create. So here is topo. This topo that is the linear topo I just created, right? And I assign this Mininet object created with topo to the net variable. Then I put net.start, which is the command to start the topology. And I will print the connections that I can use with the net.hosts. Okay, all these, let's say, methods are actually in the OpenFlow API that I showed you in the previous class. And I can also actually run some normal commands that I can use in the CLI. I can use it here. For instance, I can do the ping goals in the net and net.stop. Okay. And here is just the main method, which will tell Mininet to print information in this set block level, and then run simple test, which is this function that runs all the information that all the code that I already showed you. So this linear topology will be called exercise.code1.py. You have this exercise in the website of the course, so you can actually play with this code, changing things to see how it works, right? And the idea is that you can connect the virtual machine. Here I am connected to the virtual machine, and I already transferred the file to the virtual machine, this exercise code 1.py. So if I see here in the virtual machine, I have the code here, and I can run this code. Let me run the code so you can see how it works. And let me show you here the code while I am running it. So here I can run it as sudo Python command, right? I am just running a Python program. As you can see here, I will run it. It will create a topology of 4 hosts, 4 switches. It will connect the switches and the hosts as it should, host 1 with switch 1, host 2 with switch 2, 3 with switch 3, host 4 with switch 4, and the switches, each pair of switches, S1 with S2, S2 with S3, S3 with S4. Then I will go to the simple test. This is the net start. So we are here. Let me put this a little bit smaller. And then I will print the connections with the dumb node connections method. I mean, that is already here imported. And I will show the connections of the network. So in the network, he will show me that the host 1 has the ATH0 and is connected to switch 1. Host 2, HTH0 with connected with switch 2. Host 3 with switch 3, and host 4 with switch 4. Okay. Those are just the connections of the hosts, not the connection of the switches, right? Then I can see the ping hole, and I see here is basic topology. I have connectivity between each host, between all the hosts, all the pair of hosts, H1 with H2, H1, H3, H1, H4, and all the other possibilities. And then the net dot stop, so I stopped all the network, and this is done. So this is actually a linear topology, which was programmed by me or customized by me here, right? So the idea now is that you will create another topology, a code, a skeleton of a code that I will provide here to you. And you will create a FAT3 topology. It's a common topology in a data center network. And hosts connect to the topology to the rack switches, which form the leaves or edge of the tree. One or more switches form the root, and then you can have one or more layers of aggregation switches to form the middle of the tree. This is the normal FAT3 topology. So the assignment that you will do is the following one. In this assignment, your task is to create a simple tree topology. So you will assume each level core, we will have core level, aggregation level, edge level, and the hosts to be composed of a single layer of switches of hosts, depending on, I mean, in the host level, you will have hosts, and the other levels, you will have switches. And they will have a configurable fan-out value. The fan-out is the number of connections that come out from one switch. So for instance, here, this is a simple tree network having a single layer per each level and a fan-out of 2. So you have always have one switch in the core, and as it has a fan-out of 2, it is connected to 2 switches of the aggregation layer. So one switch here, another switch here, and as the fan-out is 2, each switch is connected to 2 switches in the lower layer, which is the edge layer. And each of these switches is also connected to one host in the host layer. So your task will be to create this topology with any k value that I give you, right? So in this exercise, we will have a file that is called custom topo. It's a skeleton class which you will update with the logic for creating the data center topology described above. The skeleton class takes the following arguments as input, and this is important. I will give you some arguments for creating the links, but this will be hard-coded there. So the link ops1 will be the performance parameter for the links between core and aggregation switches. Link ops2 will be the performance parameters for aggregation and for the links between aggregation and edge switches, and links 3 upstream are the performance parameters for the links between edge switches and the hosts. The fan-out will be also a parameter to specify which is the fan-out value. Okay. So, sorry. Here, I will show you now the file, the custom topo file. So you will have here a custom topo class that you had to fill. that also inherits from the topo class. Here you have as input parameter the links opt 1, 2, 3, the fan out, and the opts. The links opts 1, 2, and 3 are actually parameters that you can pass to the add link method. So you can use the add link method with the, for instance, the switch 1 connected to switch 3, and if you pass links opt, this link will have the links opt performance parameters. For instance, here is a bandwidth of 10 megabits per second for links opt 1, delay 1 millisecond, loss probability of 0.1, maximum queue size of 100, and use of the hierarchical token bucket queuing discipline. These are just link parameters, okay? So depending on which link you are creating, you have to put one parameter or the other. Then I can call the topo with custom topo with all these parameters and the fan out. I can change the fan out here to have a bigger network or a smaller one. Here is 3, but I can change it, right? Then I will do the Mininet topo. This is just the testing part of the topology. Your logic should be here, right? The creation of the network should be here. And then I will do a pingle here and an iperf, which actually measures the bandwidth between different between actually connections between different hosts. So I would like to see what is the bandwidth taking into account the options that I put in each type of link, or that you guys put in each type of link. So this is the task, the exercise that you have to do. And if you have any question, I will be here to answer it. Thank you very much. And with this, we actually finish the, let's say, this overview of Mininet and a little bit of hands-on of Mininet. Thank you very much.